In our last episode, we drifted through the golden domain of Saturn, a realm of rings, moons, and atmospheric wonders that transformed our understanding of giant planets. Saturn's secrets, unlocked by Voyager's pioneering flybys, only deepened the mystery of what might await farther out, in the remote, dim regions where sunlight is little more than a memory. Tonight, we continue the journey outward with Voyager 2, the only spacecraft ever to explore Uranus up close. This flyby, though brief, would fundamentally reshape how we view ice giants, not only within our own solar system, but throughout the galaxy. Tonight, let's follow the arc of science, engineering, and cosmic curiosity that brought Voyager 2 to Uranus, and see how a few hours of close observation opened decades of new questions. After its triumph at Saturn in August 1981, Voyager 2 embarked on a lonely 5-year interplanetary cruise, one of the most challenging stretches of robotic exploration in history. The spacecraft, already operating long past its original design life, coasted in near-total darkness, its faint radio signal requiring the full power of NASA's Deep Space Network to hear its voice across the deep. Every aspect of Voyager's long voyage demanded extraordinary foresight. Navigation was an act of high-precision art. At the vast distance of Uranus, even a tiny miscalculation would send the probe millions of kilometers off target. Mid-course correction maneuvers, tiny burns using the spacecraft's hydrazine thrusters, were planned months in advance, then executed autonomously, their results checked by measuring the Doppler shift in Voyager's carrier signal from Earth. The spacecraft's systems, designed for a nominal 4-year mission, now faced their second decade in space. Power from the plutonium RTGs was steadily declining, requiring careful rationing and timed instrument checkouts. The scan platform, the movable neck on which Voyager's cameras and spectrometers were mounted, had developed glitches due to years of cosmic ray exposure, forcing engineers to create contingency programs to ensure it would work for Uranus's crucial observations. With each new kilometer, the radio link grew fainter. It now took more than 5 hours for a signal to make the round trip between Earth and Voyager 2. Commands for the Uranus flyby, every scan, exposure, and data sequence had to be coded, tested, and uploaded months before the encounter. Before Voyager 2, Uranus was the most mysterious of the classical planets. Discovered in 1781 by William Herschel, Uranus was the first planet found by telescope, doubling the size of the known solar system. Yet 2 centuries later, it remained a cyan blur in distant telescopes, with few known moons, a recently discovered ring system, and an extreme tilt, rotating almost on its side with an axial inclination of 98 degrees. Why was Uranus tipped so far over? What were its rings and moons like? How did its interior compare to Jupiter and Saturn? Could Uranus help us understand ice giants across the universe? These questions shaped every choice as the Voyager team scripted the flyby. The trajectory itself was dictated by science and necessity. To maximize the value of a single pass, Voyager would aim for a close approach, just 81,500 kilometers from the cloud tops, while crossing the ring plane and targeting Miranda, Uranus's enigmatic inner moon, for a close flyby. The geometry meant only one hemisphere of each major moon could be imaged in detail. This trade-off was accepted for the sake of ring and magnetic field science. Encounter planning focused on maximizing unique measurements, imaging both the sunlit and backlit sides of the rings. observing radio and stellar occultations to probe the atmosphere and ring structure, and timing observations to catch occultations and mutual events among the moons. As Voyager neared Uranus, the mission team faced daunting technical constraints. At nearly 3 billion kilometers from Earth, Voyager could send data at only 21.6 kilobits per second, slower than an old dial-up modem. Every image, spectrum, and plasma readout was prioritized in a long, carefully ranked sequence. Key insurance images were sent first, in case of spacecraft faults or sudden loss of contact. The spacecraft's scan platform, already showing signs of mechanical aging, required delicate programming to rotate smoothly through thousands of pre-scripted moves, imaging the planet, then slewing to the rings, then tracking each moon as it swept by. The risk of a stuck platform was real, so backup safe modes and real-time monitoring routines were uploaded, ready to override or reset the scan commands if needed. The Deep Space Network maintained 24/7 coverage with its largest dishes in Goldstone, Madrid, and Canberra, combining signals for maximum clarity. A faint carrier tone, less than a billionth of a watt, carried all the scientific treasures back home. Voyager 2's flyby on January 24th, 1986, revealed a planet both muted and mysterious. Uranus's pale blue-green color, captured in haunting images, arises from methane in the upper atmosphere. Methane that absorbs red light and reflects blue. Voyager's ultraviolet and infrared spectrometers revealed the composition and structure of Uranus's cold, dense atmosphere. They found that hydrogen made up the vast majority of the planet's air, accounting for about 83% by number, while helium contributed around 15%. Methane, though present at only about 2%, was responsible for almost all of Uranus's visible color, casting its characteristic blue-green hue. In addition to these main components, the spectrometers detected traces of other molecules, acetylene, ethane, and even more complex hydrocarbons formed high in the atmosphere through the action of ultraviolet sunlight, a delicate chemistry that produces the faint, hazy layers shrouding the planet. The atmosphere was found to be staggeringly cold. Upper-level temperatures reached only -214 degrees Celsius, making Uranus the coldest known planet. The cloud structure was unexpectedly simple. Only faint bands and subtle streaks, almost invisible compared to Jupiter and Saturn's riot of storms. Yet beneath this calm facade, Voyager detected atmospheric winds moving up to 250 kilometers per hour, subtle but fast. The winds reversed direction with latitude, creating a pattern different from any other giant planet. Later Hubble and Keck observations, decades after Voyager, would reveal that Uranus's weather is highly seasonal. Storms and bright clouds appear as each pole slowly swings into sunlight over the course of its 84-year orbit. Most puzzling, Uranus emits almost no excess heat, whereas Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, due to heat left over from their formation and ongoing internal contraction. Uranus's thermal output is almost exactly balanced by the sunlight it absorbs. This suggests its interior is either uniquely insulated, or that some past cataclysm, perhaps the impact that knocked it on its side, stifled its internal heat flow. Voyager's infrared data and atmospheric occultations revealed complex haze layers and a deep methane cloud deck near 1.2 bars pressure. Ultraviolet sunlight breaks apart methane molecules, forming a photochemical smog that settles as a thin hydrocarbon haze. further muting any visible cloud features. Before 1977, Uranus's rings were unknown. Their discovery came when astronomers observed a star briefly blink out several times as Uranus passed in front, a sign that something, perhaps narrow rings, was blocking its light. Voyager 2's flyby confirmed the reality and nature of these structures. Unlike Saturn's bright, broad rings, Uranus's rings are narrow, sharp-edged, and dark as charcoal. Voyager imaged 11 main rings, some just a few kilometers wide, each composed of icy particles, ranging from centimeters to meters in size, coated with radiation-darkened organic material, tholins, formed by the slow action of cosmic rays and solar UV. Voyager's photopolarimeter detected even fainter, dusty rings outside the main ring system, features too tenuous for cameras to see directly. Backlighting by the sun during the ring plane crossing allowed the spacecraft to measure fine particles and search for micromoons. Some rings show striking sharpness, their boundaries maintained by the gravitational pull of shepherd moons. Voyager discovered Cordelia and Ophelia, two such shepherds, orbiting just inside and outside the brightest ring, Epsilon. The ring's darkness, lack of dust, and structural precision suggest they are relatively young, possibly formed by the breakup of a moon or the impact of a comet within the last 100 million years. Occultation data showed vertical structure in the rings, tiny waves, clumps, and kinks that may result from moon-ring interactions or past collisions. Voyager 2's magnetometer, plasma detector, and cosmic ray instruments uncovered one of the most remarkable and unexpected findings of the entire mission. Uranus's magnetic field proved to be utterly unique, unlike any that had ever been observed. Instead of being neatly aligned, the planet's magnetic axis is tilted by a dramatic 59 degrees from its rotational axis, and even more surprisingly, the field itself is offset by nearly a third of Uranus's radius from the very center of the planet. As Uranus slowly rolls along its distant orbit, this tilted and displaced magnetic field doesn't stay fixed. It tumbles, causing the entire magnetosphere to spiral and corkscrew through space in a wild, ever-shifting dance. During its passage, Voyager crossed the boundaries known as the bow shock and the magnetopause, precisely mapping where the relentless flow of the solar wind collides with and is deflected by Uranus's magnetic bubble. Within this magnetosphere, Voyager discovered radiation belts, not as intense as Jupiter's, but still significant, where electrons and ions trapped by the twisted field slowly weather and darken the planet's rings and moons over time. And there were auroras too, though these were patchy and irregular, not anchored to either the magnetic or rotational poles as on other planets, but flickering at unexpected locations, their patterns shaped by charged particles streaming along the tangled field lines, and, at times, focused by dynamic interactions with the solar wind itself. Theorists now believe that Uranus's magnetic field arises not from a metallic core, as in Earth or Jupiter, but from convection in a thick shell of supersonic water ammonia slush above the rocky core. This is the first real-world evidence for a whole new kind of planetary dynamo, a model now applied to ice giant exoplanets across the galaxy. The magnetotail of Uranus, observed by Voyager, stretches millions of kilometers downwind from the planet, twisted into a long helix by the planet's off-center rotation. This feature, invisible from Earth, showed that ice giant magnetospheres could behave very differently from those of gas giants. Prior to Voyager, Uranus was known to have 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. The flyby discovered 10 more, all small and faint, orbiting close to the planet. The imaging of Uranus's 5 major moons proved nothing short of revelatory, as Voyager's cameras brought into focus worlds that had previously been little more than points of light. Yet, the encounter's geometry allowed the spacecraft to photograph only the hemisphere of each moon facing it during the fleeting flyby, leaving half of every surface still uncharted, even today. Among these moons, Miranda stood out as perhaps the most bizarre small world in the solar system. Voyager's close images unveiled a landscape unlike any other, scarred by gigantic fault canyons and oval-shaped structures known as coronae, and home to the tallest known cliff, Verona Rupes, plunging some 20 kilometers. Miranda's surface appeared patchworked, as if it had been assembled from fragments. A landscape shaped by episodes of violent disruption and gravitational reassembly. Or perhaps by the powerful forces of tidal heating and resurfacing. Ariel, by contrast, displayed the youngest and brightest terrain. Its surface, marked by few craters, gleamed with bright canyons and carried signs of relatively recent cryovolcanic flows, with some regions believed to be only a few 100 million years old, possibly created by ammonia water eruptions that hint at a history of internal warmth. This evidence has made Ariel a prime candidate for being an ocean moon, with some models suggesting it could still harbor a hidden sea beneath its icy shell. Umbriel, on the other hand, is the darkest and oldest of the 5. Its surface is cloaked in carbon-rich material, and it bears a striking feature within the large crater Wunda, a mysterious bright ring that might be freshly exposed ice from a recent impact, offering a rare contrast on its ancient, shadowed landscape. The 2 largest moons, Titania and Oberon, reveal a blend of histories, with ancient, heavily cratered regions interrupted by younger fractures, chasms, and scarps. Their densities point to a composition of both ice and rock, and signs of past geological activity suggest that internal heating or orbital resonances may once have stirred their interiors. Collectively, these snapshots from Voyager revealed a family of moons shaped by dynamic processes, each one a unique testament to the power and variety of planetary evolution at the solar system's distant edge. Voyager's data revolutionized the study of icy moons. Instead of static relics, Uranus's satellites revealed histories of tectonism, cryovolcanism, and perhaps even subsurface oceans, key elements in the search for habitability beyond Earth. Every aspect of Voyager 2's encounter with Uranus was defined by constraint and risk, the mission unfolding under the pressure of an aging spacecraft, a scan platform that had begun to falter, steadily declining power reserves, and the severe limitation of a low data rate. These realities forced the mission team to make hard choices, setting science priorities with relentless discipline. Only a fraction of the desired images and spectroscopic measurements could be sent to Earth in real time, so each data slot was precious. High-priority targets, such as close flybys, critical occultations and ring crossings, received the first chance for transmission, while some planned observations had to be sacrificed to ensure the most valuable data would make it home. At times, the scan platform would stick or refuse to move on schedule, prompting engineers back on Earth to send backup commands, their only feedback coming from the faintest trickle of engineering data, a tenuous lifeline stretched across the void. The spacecraft also had to survive the perilous passage through Uranus's ring plane, speeding along at 15 kilometers per second. the team weighed the real risk of collision with unseen debris, ultimately judging the science returned to be worth it. Voyager emerged unscathed, but the knowledge that even a pebble could have ended the mission in an instant lingered in every decision. During closest approach, the spacecraft operated almost entirely on its own, running through thousands of preloaded commands with no possibility for real-time intervention. Every observation and line of code was the result of months of planning, built upon decades of collective experience in the subtle art of deep space operations. Yet, for all its triumph, Voyager 2's brief flyby left immense gaps in our understanding. Without an atmospheric probe, the deep composition of Uranus's atmosphere, its noble gases, isotope ratios, and the true nature of its weather beneath the upper clouds remained out of reach. Only the half of each major moon could be imaged, and just one side of Uranus itself studied in detail. The 6-hour encounter provided only a fleeting snapshot, leaving Voyager unable to observe seasonal changes, the slow evolution of storms, or the migration of atmospheric bands and ring features across years and decades. In the time since, astronomers have continued to watch Uranus from afar, using ground-based observatories, the Hubble Space Telescope, Keck, and the VLT to extend Voyager's legacy. New faint rings and arcs have been discovered, while the familiar rings have shown subtle, decade-scale changes in brightness and structure. As sunlight slowly returned to Uranus's northern hemisphere, dramatic atmospheric changes have appeared. Bright cloud outbursts and polar brightening that Voyager never saw. And the census of Uranus's moons has grown as well, with 9 more discovered, including some that may be lost satellites embedded within the rings themselves. Each new discovery underscores just how much remains to be explored, and how Voyager's brief visit was only the opening chapter in the study of this enigmatic, distant world. Voyager's legacy extends far beyond our own solar system. Since the 2010s, astronomers have discovered that most exoplanets found by Kepler, TESS, and JWST are sub-Neptunes, or mini-Neptunes, planets with thick hydrogen-helium envelopes and sizes between Earth and Neptune. Uranus is the closest analog we have, and the science from its flyby is foundational for interpreting the spectra, structure, and atmospheric chemistry of these distant worlds. Voyager's data forced theorists to expand models of planetary interiors, adding superionic water ammonia mantles, stratified compositions, and the possibility of deep, stifled heat. The strange magnetic field and ring moon dynamics seen at Uranus have become templates for understanding what may be happening on hundreds of billions of exoplanets throughout the Milky Way. For planetary scientists, the Uranus flyby remains unfinished business, a tantalizing glimpse that left as many questions as it answered, in recognition of just how much is left to discover. The 2022 Planetary Science Decadal Survey ranked a Uranus orbiter and probe as NASA's highest priority flagship mission for the coming decade. Such a mission would offer a sweeping, years-long exploration, mapping both hemispheres of the planet and all its major moons, sending a probe deep into Uranus's atmosphere to finally reveal its hidden composition, and observing the intricate dance of the rings and magnetosphere not in a single pass, but through the slow unfolding rhythms of Uranus's long seasons. The science goals stretch across nearly every frontier of planetary exploration, measuring the deep atmospheric makeup with its noble gases and isotopes unraveling the fine structure of its clouds and monitoring weather and climate patterns across the changing decades. High-resolution imaging would reveal the unseen sides of every major moon, searching for signs of active geology, the faint traces of plumes or the unmistakable hints of subsurface oceans. Those ocean worlds that may harbor more secrets still. The mission would track their evolving rings, the formation of new moonlets, and the migration of dusty bands, while also probing the very origin of Uranus's dramatic tilt and what it means for the birth and transformation of planetary systems throughout the cosmos. Voyager 2's flyby of Uranus stands as a singular moment in planetary exploration, a fleeting encounter that turned a remote, pale blue dot into a world alive with dynamic weather. A magnetosphere that tumbled and spiraled unpredictably, razor-sharp rings and moons that bore the scars of ancient upheaval. Every decision along the way, from the trajectory and instrument settings to the careful triage of precious data, was a balancing act between risk and reward, and a testament to the ingenuity required to stretch aging technology to its very limits for the sake of discovery. The true legacy of that encounter lives on not just in the thousands of images and spectra it returned, but in the doors it opened for future generations. Uranus is now recognized as a key to understanding the ice giants that fill our galaxy. Its moons may yet prove to be among the most promising havens for hidden oceans and the processes that make worlds alive. The mysteries it presented, still unsolved after nearly 4 decades, are a standing invitation to return, to delve deeper, and to uncover how the universe builds its most enigmatic and overlooked worlds. As Voyager 2 continued onward to Neptune and eventually to the stars, the data it sent back from Uranus has continued to ripple through the fields of planetary science, astrophysics, and the ever-evolving search for life. In that silent, spinning blue-green world at the far edge of sunlight, we found not only a planet, but a challenge to our assumptions, a gentle prod to rethink everything we believed about how worlds could form and change, and about our own ability to explore the unknown. In our next episode, we will follow Voyager to Neptune for its final planetary flyby before it plunges outward to the very edge of the heliosphere and into the mysteries of interstellar space. For now, as you rest beneath the slow-turning sky, remember, even in the coldest, darkest reaches, stories are waiting to be told, and new worlds await just beyond the horizon.